For our example here, we're going to find the local maximum and minimum values and saddle points, if any, of the function fxy equals xye to the negative quantity x squared plus y squared over 2. First, we'll find our first partial derivatives. You should confirm on your own that fx of xy is equal to ye to the negative quantity x squared plus y squared over 2 times 1 minus x squared. And fy, the partial with respect to y, of xy is equal to x e to the negative quantity x squared plus y squared over 2 times 1 minus y squared. Based on these expressions, if fx is equal to 0, right, the partial of f with respect to x, then y equals 0 or x equals plus or minus 1. If the partial with respect to y is equal to 0, then x is equal to 0 or y is equal to plus or minus 1. Now, we don't get to just go mixing and matching all the x's and y's that we see here. What we need are points where fx and fy are 0 simultaneously. Because fx has a factor of y and fy has a factor of x, we can see that one of the critical points is 0, 0. We can also see that because fx has a factor of 1 minus x squared and fy has a factor of 1 minus y squared, that plus or minus 1 represent more critical points. And in fact, this represents 4 critical points because we would have 1, 1, 1, negative 1, negative 1, 1, and negative 1, negative 1. In all of those cases, the factors 1 minus x squared and 1 minus y squared zero out, and therefore fx and fy are both 0. But if we consider something like 1, 0, then what we're saying is x is 1 and y is 0. And if that's true, then fx is clearly 0 because it has a factor of y. Fy, though, has a factor of x, and so that factor is 1. And another factor, 1 minus y squared, and that would go to 0 only if y is equal to 1 or negative 1. And so if x is 1 and y is 0, we're not going to zero out fy. And so fy is not zeroed when x is 1 and y is 0. My gosh. In other words, 1, 0 is not a critical point. And neither are any other combinations of x and y if only one of them is 0. Now, I just noticed that I missed a parenthesis here in my exponent, e to the negative quantity x squared plus y squared over 2. I forgot the end parenthesis there. Folks, we have all our critical points, 0, 0, and plus or minus 1, plus or minus 1. So let me just move this out of the way here. Now we need to find the value of d. First, we're going to find the expression for d. And for that, we need fxx, fyy, and fxy. I will again leave it to you to confirm that fxx is equal to xy e to the negative quantity x squared plus y squared over 2 times negative 3 plus x squared. Likewise, fyy is xye to the quantity negative x squared plus y squared over 2 times negative 3 plus y squared. fxy is e to the negative quantity x squared plus y squared over 2 times 1 minus x squared times 1 minus y squared. It's a great algebraic exercise for you to confirm that you get these same expressions. I'm not being facetious, it really is. Now, d, you'll recall, is equal to fxx, fyy, minus fxy squared. Once again, you should confirm that d of xy is equal to e to the negative quantity x squared plus y squared times the quantity x squared y squared times x squared minus 3 times y squared minus 3 minus 1 minus y squared quantity squared times 1 minus x squared quantity squared, end bracket. I know this is going by really fast here, but hey, you have the ability to pause it and go back and make sure that you see all the algebraic steps. I'm really focused more on what we do at this point. You see, we have critical points, 0, 0, and plus and minus 1, plus and minus 1. So we need to know what's going on at d of 0, 0, and then also at d of plus or minus 1, plus or minus 1. Normally, I would break these apart into their separate points, 1, 1, 1, negative 1, and so on. But if you notice, every time x and y show up in d, they're squared. And so we'll always get the same answer, whether it's plus or minus 1 for x and for y. If x and y are 0, are both 0, then e to the negative x squared plus y squared is 1. The x squared y squared factor inside of the brackets zeroes out the first term. And we're left with minus 1 times 1. I don't really care that the value is negative 1. What I care about is that it's negative. And since d of 0, 0 is negative, then we know that 0, 0 is a saddle point. D at plus or minus 1 plus or minus 1 is going to give us e to the negative 2. That's a positive value. And then inside the brackets, we have 1 times 1 minus 3 times 1 minus 3. So that's a positive term. Minus 0. And so d of plus or minus 1 plus or minus 1 is positive. At this point, now we need to know what's going on with fxx. Well, fxx is way up here. And I'm just going to go ahead and make use of this technology and copy and paste it. Now notice that for fxx, we have a factor xy, and then e to the negative x squared plus y squared over 2. That will always be positive because e is a positive base. And then we have negative 3 plus y squared, negative 3 plus x squared. And whether x is a positive or negative 1, that's a negative value, right? So what we have is xy times a positive number times a negative number. Therefore, fxx, if the signs match for x and y, so 1, 1, and negative 1, negative 1, are both going to be negative. Fxx at either 1, negative 1 or negative 1, 1, that's going to give us a negative for the first pair of factors, and then positive times negative, and so is positive. For a d value that's positive and a second derivative, fxx, that's negative, now I'm thinking about in R2, negative second derivative, concave down. There's a local max at 1, 1 and at negative 1, negative 1. If d is positive and fxx is is also positive, then again I'm thinking about concavity in R2. Second derivative being positive, we're concave up. So we have local minimum values at 1, negative 1 and negative 1, 1. But knowing where they are does not tell us what they are. For that, we go back to the original function. fxy was given to be xy times e to the negative quantity x squared plus y squared over 2. The function f at 1, 1 will turn out to be the same as the function f at negative 1, negative 1. And you can confirm that that's e to the negative 1. f at negative 1, 1 is equal to f at 1, negative 1, and they equal negative e to the negative 1. We already concluded that we had a local maximum at 1, 1 and a local maximum at negative 1, negative 1. And here we can say that the local maximum value is e to the negative 1. Likewise, we had confirmed that we had a local minimum at 1, negative 1 and another one at negative 1, 1. Now we can conclude that the local minimum value is negative e to the negative 1. So that you can see what's going on, I have a graph here in GeoGebra of our function. And here's the positive x-axis pointing to the left, positive y-axis pointing to the right. And so this peak here is associated with the point 1, 1. We also see another peak associated with the point negative 1, negative 1. And likewise, there is underneath the fourth quadrant a trough, I'll call it, and also underneath the second quadrant a trough. Those are associated with 1, negative 1 and negative 1, 1. Here near the origin, what we see is that crossing from the first quadrant to the third quadrant, the origin represents a local minimum. Excuse me, not a local minimum, but a minimum value for that path. But if we cross from the second quadrant to the fourth quadrant, it's a maximum in that direction. So that's the picture of a saddle point there at 0, 0.